last night, but I did have one question that popped up while
Okay.
I was doing that. Cool. It's about the isomorphic graph question. And the way I did that one was by drawing out the graphs and kind of analyzing them that way. But I seem to remember us discussing something about you could look at the adjacency matrix and decide from the two adjacency matrices whether or not the graphs were isomorphic to each other or not. But I don't really remember the method for that. Did I make that up, or
No, that's effectively true. But it's easy to say and tricky to do.
okay?
So to be isomorphic, we need a bijection between vertices that preserves adjacency, right? So if we have
I'm confused exactly how it looks ahead.
oh what?
I'm confused exactly how it looks ahead. I mean, like, you go to the closest node, right?
Oh, Dijkstra?
Yeah.
Let's come back to it.
Okay.
Let's finish this thought first. So adjacency matrix, right? A is adjacent to B, and C. B is adjacent to A, and D. C is adjacent to A, and D is adjacent to B and C. And for this other one, I is adjacent to J and L. J is adjacent to I and K. K is adjacent to J and L. And L is adjacent to I and K. Probably made horrible mistakes in here, but we'll live with it. So we need a one-to-one mapping between these and these, such that we preserve adjacency. Well, if we decide to map A to J,
Let me see, I to K.
well, for example, if we want to map A to J, right, that's really just taking this row and moving it down here, and taking this column and moving it over here. In other words, swapping rows and columns. So what is it actually? A. So I think that'll end up being our isomorphism. So asking if there's a bijection between vertices that preserves this adjacency is equivalent to saying, can we arrange the rows and columns of this to end up with this? And that's not easy to do, but if you can do it, then you can say they're isomorphic.
Okay.
The other thing you can do is you can start to figure out things like degrees of vertices, and we can see we have degree 2, 2, 2, 2. If we had any degree over here that was different from 2, right away we could say they're not isomorphic.
Okay.
So you can do the negatives by analyzing invariants like degree, or you might actually find an isomorphism by rearranging rows and columns.
But when trying to determine what the bijection is, it might be easier to go with the graphical approach.
Yeah, if you're a human, you tend to be good at processing visual manipulations like that, as opposed to, you know, if I do this and this, then this is going to look like this.
Okay, cool.
But if you were trying to program a computer, it might be more direct like that.
All right, that was my question.
All right. class. So in this case, just swapping those last two rows and the last two columns should turn this into this. I believe it. Yeah.
You also have to swap the columns.
Yeah.
Too. But that might be a while.
So I'm coaching about PA3. I don't know if it's the right time to ask it.
Let's do Dijkstra and then we'll do PA3. So you had a Dijkstra question, Sage?
Yeah.
Okay.
You go to the closest node,
Mm-hmm.
but then what do you do?
Then you fill in its tentative distance,
It's distance from.
right? So you found a node here that was closest to your visited nodes. So if this was a distance of 3 and this edge is a distance of 4, then you know you can get here in no worse than 7, right? Because in 3 hops you can get to here, and in another 4 you can get to this node. So you relax this distance. If it was currently something bigger than 7, change it to a 7. If it was smaller, then and replace it. And do that for all of the nodes connected to this one that you just visited. Okay, so you find your closest node, you add it to the visited list, and then relax all of the connected nodes. And then go back and find the node closest to the new set of visited nodes.
I'll work on it.
Okay.
By myself a little bit because it's just confusing.
So yeah, so you have a set of visited nodes. Pick the node that's closest to any one that you visited. Right, so if it's this one, fill in its weight and then relax everything that's connected to it. And then go back and do it again. Yeah, try it with an actual graph.
Okay.
PA3.
So basically, I was trying to use getchar or getC standard name to read unlimited vertices.
Okay.
But the problem is that it's going to put additional characters to that, to the end of the character. So it's not just single character.
Okay. So you're trying to read a pair of vertices.
That's right.
Okay. Your best bet for reading in numbers, well, you got 2 options. If you assume that the person's not going to make any mistakes and not going to do anything weird, you can use scanf. Right, that says pick up the next 2 integers from standard in, convert them to integers, store them in from and to, which are defined to be integers, and if that returns a 2, you know that it picked up 2 integers. If it doesn't return a 2, then something wasn't an integer, they typed a letter, perhaps.
So if it's integer, it's gonna return 2.
If both of these are converted to integers, it will return a 2. Because I'm asking it to convert 2 things from standard in. If it only converts 1, it'll return a 1. If it doesn't convert any, it'll return a 0.
Yeah, the return from scanf is literally the exact number of things that it was able to successfully convert.
Right. And then if they hit Control D, it'll return either 0 or it might return -1. I don't remember. I don't do scanf. But write some code and figure out.
Can we also show user something like parentheses and comma between them?
Yeah.
Can I show that?
So if you want them to enter this format,
Yes.
scanf will let you do that. You can say dash. And if they don't type it like this, it'll throw up. Right, it'll say 0 things converted.
How do you get it to detect if there's just a blank line in it?
If it's just a blank line, I don't know if scanf will let you do that. Because white space, it won't come back and fail, it'll wait for more input. So what you probably want to do is use fgets. So right, make a string array that's big enough for your input. Fgets array length standard in. As soon as they hit enter, this will be whatever they typed. If they just typed an enter with nothing else on the line, this will be a string consisting of one character, which is a new line. If they type parentheses 5, comma 2, then that'll be what's in your buffer.
If you do the same if test on scanf and just ask it if it returns 0, would that work too?
I think if you just hit enter, it won't come back
It won't come back.
from scanf, because I think it considers that to be white space. But I'm not positive. You can try it. Try it with that. Just hit an empty line, see if it works. If not, then switch to scanf. Alright, so do your fgets and then do an scanf, which says do scanf on that buffer.
Is that okay if we limit that to 120 or like 1,000, some limited numbers?
Yeah, unless they're going to have vertices that are like 100 digits long.
Oh, so this is just for any
This is just for
single
one line. Yeah.
Is there an analog for scanf other than cin for C++?
Other than what?
Cin.
Oh, yeah, I think so. Plus scanf works in C++.
Oh.
Should. But again, write junk code, right? Just write a snippet of code and play with the pieces you're going to put together and figure out how they work and how to make them do what you want. And then put them together in your actual program. Break it up into subproblems as appropriate. Other questions? Yeah.
So the two numbers for input, is that like the number of the nodes, or is that the coordinates of the nodes,
It's the number of the vertex of the node.
of the vertex?
Yeah, so just imagine these things are numbered from 1 through n or from 0 through n. It's up to you.
Okay.
And if you want to connect an edge between vertex 2 and 5, you would type in 2 space 5, enter. And that's saying there's an edge between 2 and 5. If you wanted it between 2 and 1, type in 2 space 1 or 1 space 2, enter. And so you type in all these pairs of vertices, and you're saying this is where all the edges are. When you hit an empty line without typing any numbers, that says that's all the edges I have. And from that you can build your matrix and do the analysis.
You were making the adjacency list that we did, I think, Friday? I think that's when we did the
I think
adjacency
so,
list
yeah.
in class. Yeah, and it's just like the set of all the vertexes that are adjacent to each other.
Okay. So watch the video again.
Okay.
So we're not trying to connect the nodes, we're already given every single
You're
connection.
given what the connections are, yes.
Okay.
That's what the pairs are that you input. It means there's an edge between
That was one
those
of
two.
the things I was thinking, was like, these were coordinates, and I'm like, well, how do I discern which ones are connected and which ones
Nope.
aren't?
Yeah, so if this is 0, 1, 2, 3, right, I'd say 0, 1, 1, 3, 3, 2, 2, 0. That would be my graph. Yeah.
I'm not sure if it's a valid question anymore. If you were to say do this with structs, could you have like an array of structs within the structs defining edges from that point?
Sure.
Okay.
Yeah. So you could make a struct for an edge that would have 2 integers, a from and a to, and then you could make an array of those. But part of the assignment is to print out the adjacency matrix. So you're going to have to build an adjacency matrix anyway. So if you want to store it directly as an adjacency matrix, that might be less work. But if you want to store it as an array of
Not much fun.
edges and then create it, that's fine too.
One more question. scanf is closing, you're gonna need to press enter, right? But enter is also the terminator, so it's just going to read one pair.
Wait, say that again?
So after each pair, we're gonna need to press enter, as is the scanf.
Right.
But when we press enter, it's gonna be end of the program, basically end of the reading things, end of all the pairs.
No, it's just the end. If they just hit enter with nothing else, yes, that's the end of all the input.
Okay. So
But you hit 5 space 2 enter or parentheses 5 comma 2 print enter, and that's one pair of vertices. And then you can type 2 space 3 hit enter, and that's another vertex.
okay.
And after this one, you just hit enter without putting anything else on the line. It should detect that. That's when you know you've got all the vertices.
That's a good piece problem.
Okay, write a program that just does that. Just lets you input integers, and when you hit an enter with nothing on it, it says, okay, you're done.
Okay.
And it's easy to do if you're using FGETs. It's easier to do if you're using FGETs. Because if you just hit enter, buffer will be exactly equal to just a single character line containing a new line. So it could be as easy as just checking string length on buffer. And if it's equal to 1, they must have just hit enter.
That's right.
Or do a string compare to \n. See if it returns 0. If it does, then that's exactly what they entered. Anything else? All right, let's wrap up talking about graphs. And maybe start languages. Maybe not. So, let's talk about spanning trees. So a spanning tree of a graph G is a subgraph of G. And remember, a graph is a set of vertices, a set of edges, so a subgraph is a subset of those vertices and a subset of those edges. It's a subgraph of G that contains every vertex of G. Cool. And is also a tree. So it has a root and it has no loops, and it's connected.
Sorry, subgraph, is that just like a branch of the tree that's contained in the larger
Yeah.
graph? Okay.
So it's a subset of the vertices and a subset of the edges.
Okay.
It has all the edges and vertices that G has.
No, it has all the vertices, does not have all the edges. I mean, a subgraph could have all the
That's
edges.
possible.
Well, so there's a graph. It's definitely not a tree. A subgraph containing all the vertices, that's also a tree. I can find that basically by carefully removing edges such that I don't leave any vertices hanging. So let me redraw this so we can hack it up. So if I want to find a spanning tree, I can simply remove pieces of any cycles that I find in here. So for example, I can take out this line, but I don't want to remove BG now because then G is not going to be a part of our graph.
You can get rid of BF.
I could get rid of BF because that's also giving me a cycle. And I could get rid of anything on this cycle.
And then trim out IJ or HI.
Alright, we'll take out IJ. And we've got a tree.
Oh, yes we do.
I don't get it, like, that isn't the same graph if we just arbitrarily...
No, it's not. It's a subgraph. It contains the same set of vertices. And it contains a subset of the set of edges. So it's a subgraph. But it's also a tree.
So if it doesn't include all the vertices, it's just a subgraph?
No, it would still be a subgraph. But to be a spanning tree, it's got to contain every vertex of G. And it's got to be a tree.
And you can make these spanning trees of a given graph in different ways.
Yes.
In some situations, like if you hadn't gotten rid of HJ, but you did get rid of BG, sorry, HG,
Mm-hmm.
but you did get rid of BG.
Right. That would also, well, that would also give me a tree.
Yeah.
So that's a spanning tree.
Any number of other variables.
Yes.
Yep.
Lots of possibilities. So we can spin a theorem from this that says a graph is connected if and only if it has a spanning tree. And that's going to be true because if we have some other stuff over here, we cannot find a subgraph that's going to be a tree because trees are connected. Yeah.
We can't create new...
Can't create new vertices. It's got to be a subset of the set of vertices.
Or edges.
No,
Or edges.
no edges?
Can't add new edges either. Right, so subgraph. Right, if those are two graphs, this is a subgraph of this if and only if these are true.
Yeah, so like you could take the tree that we made and stick it on top of the original graph and you wouldn't have any extra edges.
Right,
You're just missing some.
or vertices.
Or vertices, yeah.
All right, we can also form spanning trees by picking a root and traversing outward, and we can do this two ways, depth first or breadth first. So if we decide that we want A to be our root, for example, we can simply move out from A and keep adding vertices as long as we don't create a cycle. So if we were to do this depth first, let's just say we're going to move from A to B, and then from B to C, and then from C to D, and then from D to E, and then from E to F. And then from F, we could go back to B, but that's going to give us a cycle, so we're not going to do that. We could go down to I, and that's fine. And as soon as we go to I, we're going to start looking for further paths from there. So we could go from I to H. And then from H, we could try to go to A, but that'll give us a cycle. We could try to go from H to G, and that'll work. And then from G, we could go to B, but that'll give us a cycle. So we're done with G. That's the deepest part of our process. We back up one step to H. Were there any other nodes we could go to? We couldn't do A, we did G, we're done. We back up to I, we did H, we came from F, we could go to J, so we can go to J, now we're done with I, we back up to F, and we're not going to have anything else we can connect to, and if we back all the way up, we'll find that we're done. And so that's a depth first spanning tree that we would create starting with A. we can also do this breadth first. We can begin to move, but at each point we branch off to as many adjacent nodes as we can. And after visiting all of those, we move down one level. And I'm horrible at creating breadth first spanning trees on the fly. So this is depth first.
Those both sound suspiciously recursive.
Yes, they are.
It's not recursive, it's in 222.
So there's A, we can go out to B, we can go out to H, and those are the only spots connected to A. Now we can go to B, we can visit each of its neighbors, so we can come to C, we can come to G, and we can go to F, and then we go to H, and we can go to G, but that'll give us a loop. A will visit something we've already done, and I will come down there. So this was our first depth, this was our second depth, and these are our third. And we continue, so from C we can go to D, that's a depth of 4. From F we can go to E,
I.
and we can go to I. No, we can't go to I because that'll
We already had that.
give us a loop.
Oh, it's down there, okay.
So I think F is done from G. We can go to H, that'll loop. From I, we can go to J,
Then you're done.
and then I think we're done. So there's a breadth first spanning tree.
And it seems like the breadth first tree is going to be closer to balance, in a way.
Possibly, yeah. I mean, that would sort of feel right because we're moving across before we move down.
Because if you lengthen both of these at A, and went downward, you'd
Yeah,
you'd
A's
have
like,
yeah, on the depth first, you have a lot more.
yeah.
Yeah.
That's probably a valid notion.
Well, that makes sense because you're not waiting to branch, you know. with
Yeah,
the
you're
depth first.
avoiding moving down until you have nowhere else that you can go on this level.
Yeah.
So I think that probably will be more balanced.
So when do you not care about balance?
You care about balance if you're planning to search the tree, if it's a binary search tree. If you're planning to traverse it, where you might have to go all the way down to a leaf.
Right.
The more balanced, the shallower it's going to be in general.
So when do we not care about the balance, though?
I'm not sure.
Yeah, 'cause that's what I'm wondering with the depth first approach, because it's a lot of arbitrary steps before you start branching.
On the other hand, this may be fewer. If this was a communication network, there might be an advantage to having this kind of situation versus branching off in multiple directions, maybe. Or if it were a roadway, it might represent fewer intersections,
Oh, sure.
or fewer multi-way intersections. But that's just off the top of my head.
At the cost of drastically increased time to get from location to location.
Yeah.
Unless not having any stop signs because you don't have any crossroads. Let's
If
go
if A through I is your highway, you know,
Yeah,
and then you're getting off, man, it's
it's a weak attempt, but hey, it's Tuesday. All right, the other notion is if you have weights on here, I don't know, I just made those up. We put weights on these edges and there's now a cost associated with getting from one vertex to another along an edge. And you can ask, what's a spanning tree with the minimum total weight, or the minimum total cost? A collection of edges that contains every vertex is connected like a tree, but collectively is the smallest total weight. And that's a useful question for things like communication networks, because it might be very expensive to communicate directly from B to C because perhaps there's a canyon or a river in the middle of them, whereas going through some other route might be more hops but might end up being lower cost. So a spanning tree gives you a way to connect all the nodes in your graph, which is something you'd want to do like if you're distributing Netflix through a series of customers, and you have a setup where you can send information to one customer and their box can forward it to another one, and that box can forward it. And so you have the option of redirecting from any of these nodes to any other nodes that are connected. You might want to try to find a minimum cost solution, and a spanning tree would do that. And if you're not worried about redundancy, we don't need two ways to get from A to G, we just need one. And this way would have a cost of 4, this way would have a cost of 6. So to find a minimum weight spanning tree, it's easy. So we can use something called Prim's algorithm. And this is an example of a greedy algorithm. And I'll tell you what that means in a moment. But Prim's algorithm basically says pick a lowest weight edge. So we've got a few edges with like a weight of 1. We can pick any of those. So let's just go from A to H. Pick another lowest weight edge without creating a loop.
So 2. Sorry, H to I.
Yeah, so I don't think it has to be connected.
Oh.
No, it has to be connected.
edges that
Pick
are-
another lowest weight edge.
Okay.
Connected. All right, so A, we have an edge of 4 to B, we have an edge of 3 from H to G, we have 2 from H to I, so let's go with 2. And you just keep going. So I am just going to go to F because that's a weight of 1, and I'll take my 1 over to E. And I'm out of 1, so I can start picking up any 2s. I'll just go 2 from E to J. And
F
about
to B,
F to B,
B to G,
E to G.
and we're up to 3s. It's going to be E and D. If we can't
So
do H,
E will go up to D.
and then that's everything except for C. That's going to be B and C.
And so yeah, BC will be 5, CD will be 6. So we'll go 5 over to C. Have we got all our vertices? C, D, E, F, G, H, I, J. So that is a minimum weight spanning tree.
Did you use this for pathfinding?
Yes.
Do we decide if they need to be connected or not when we're picking?
They do
ranks?
need to be
They
connected.
do need to.
Yeah.
Okay. So we pick A to H and then H to I, and then
Right.
I to F. Okay.
Mhm. You can do it for pathfinding, but it's not a path as in starting from one point, ending at a destination, right? It's still a tree. But it's a way that if you wanted to build a telephone network, this is the cost of connecting 2 points with your fiber.
Lowest total cost.
Lowest total
Taking
cost.
everything, not necessarily the lowest route.
So you have a way to hop from one node to another, so which node should we actually connect? That would be a lowest cost solution. And it's a greedy algorithm. Yeah, it does the best that it can to solve the problem at each step. Whatever it wants the lowest cost path. I'm going to pick the cheapest edge, and I'm going to add that in. And now I'm going to pick the cheapest edge from the remaining set, and I'm going to add that in. At each step, it's doing the thing that most satisfies its underlying goal. That doesn't always get you a good solution, but for Prim's algorithm, it does. It takes work to convince yourself.
Well, because moving from A to B costs 4, but moving from A to B through HG ends up costing you 5.
Right.
6.
But the total cost of this network, if you add up all these weights, is smaller than if I had a tree that included an edge from A to B.
The big key here is that it's not trying to find the cheapest route from A to B, it's
Right.
trying to get the lowest total
Cost for the system.
Yeah.
sum of the entire thing, which is not necessarily what you'd want in all cases.
Right.
So if this is a telephone network or a cable network,
And you're
got
paying per the
these-
foot of copper.
Yeah.
This minimizes your total cost.
And the guy who lives out in the boonies is just
He's got to go through 80
He
miles
lives
of
there.
copper to get his call, but
The guy who lives right next to the distribution station in G is
yeah.
calling every day to complain that his cable sucks.
Yeah.
Not Dylan.
So we touched on the knapsack problem before, right? You had a bag, you could hold a certain amount of capacity, and you had a set of items with weights and values, unlimited number of them available. If you allow fractional items, like if you're at the bulk bin at Freddy's, and you can pick out however much of each item you want, you can solve that problem with a greedy algorithm. Right? You simply pick the item that's most valuable per unit weight and take as much of that as is available. If there's an unlimited supply, that's what you fill your bag with. So if you've got gold powder and silver powder and iron powder, right, and the gold is most valuable per pound, if 5 pounds of gold is available and your capacity is 20 pounds, you take all 5 pounds of gold. And then if there's 12 pounds of silver available, you take all 12 pounds of silver. And now you got 3 pounds left, you fill that up with iron. Right? So a greedy algorithm works for this fractional knapsack problem, but it doesn't work for the knapsack problem where we have whole numbers of items that we're taking. So that's why we have to do this recursive solution to it. So some algorithms, like finding a minimum spanning tree, work well with greedy solutions. Others don't. You can do a whole course on algorithms. We'll do some of this in 222, 223, but you can do a whole graduate level course on algorithms and study these different styles of algorithms and get into actually proving them to like see that they actually work and why they work, and that's fun stuff. That's another class. Questions on graphs? All right, let's start talking about languages, because we've got about 7 minutes. So I'll give you a quiz on Wednesday that'll be basically trees and graphs. Your homework is due Monday, so I'll collect that, get it back to you Tuesday, we'll talk about it, and then quiz on Wednesday. Trees and graphs.
not tomorrow. He means next Wednesday.
Right.
Syntax syntax versus semantics. So let's look at example of a formal language. So I'm going to define a sentence. As a noun phrase followed by a verb phrase. And a noun phrase and a verb phrase are as follows. A noun phrase is an article plus an adjective plus a noun, or just an article plus a noun. A verb phrase is a verb plus an adverb, or just a verb. An article is the or a. An adjective is large or pink. A noun is dog or bacon. A verb is eat or, I don't know, give me a verb, run. Could do bark. An adverb, give me two adverbs.
Computer science majors, not English.
Quickly.
Or slowly.
Or slowly. And we've got a formal definition of what a sentence is. Right? So we can do two things with this. One, we can identify something and say whether or not it's a sentence. And two, we can use this to construct sentences. So it can be used for analysis or synthesis. So for example, a sentence is a noun phrase followed by a verb phrase. A noun phrase could be an article followed by an adjective followed by a noun. And a verb phrase could just be a verb. And so we can start making trees, because it's always a good day when you make trees.
We could also determine how many total sentences are possible in this language, right?
Yes, we could.
Yeah.
Absolutely. So here's one version of a sentence. It could be an article followed by an adjective, followed by a noun, followed by a verb. And I can construct a sentence by simply continuing this. So an article could be the. An adjective might be pink. A noun might be bacon. That's disgusting. And the verb could be, let's say eats or runs. Could be runs. The pink bacon runs.
I'm not chasing it.
Probably because the dog's chasing it.
No, it's uncooked, so it could still be on the table.
Yeah, that's true.
Still
Okay.
not chasing it.
That's a valid sentence, according to this definition of what a sentence is. It could also have been a large bacon eats slowly. That's also a valid sentence. but it doesn't have any reasonable meaning to us, right? So the syntax is perfectly fine. Syntax is defined by a formal language definition like this. Semantics have to do with meaning. And what does the sentence mean? It really means nothing. So Noam Chomsky used to use examples like the colorless green gas sleeps noisily, right? It's a perfectly valid sentence syntactically, but semantically it's gibberish, okay? We're not going to worry about semantics. We're going to be talking about syntax. In the sense of C code, for example, the compiler checks the syntax of your C program and determines whether or not it's syntactically valid. Now, if your C program says something like integer x, x equals 0, x equals 1, x equals 2, if x equals 0, x equals 0, that's syntactically valid. The compiler will look at that and say, thumbs up. But semantically, it's gibberish. This does nothing except set x equal to 2. And then we don't do anything with x. We might just, return at this point. Okay, so we're going to be looking at ways of specifying languages in terms of their syntax. We're not going to be worrying about meaning for now. Okay, so we'll start on Monday generalizing this. This was a particular example of a formal language, but we'll generalize these notions. We'll talk about vocabularies and alphabets and sentences in a more general sense, and how to describe this kind of specification of a language. And we'll use that to recognize sentences, and we'll use it to construct sentences. And this will eventually bring us back into 250. We'll end up back in state machines and see ways to think of that. Smile when I say that. All right, and it'll end up at the end of next week talking about theories of computation, basically. Turing machines and computability. So back to some of the stuff we started with. All right, I will see you next time.